Okay, everybody, thank you so much for joining us today. It's 10 o'clock, so we'll go ahead and get started. My name is Christina Ung. I'm part of the marketing team here at KETIV, and I help facilitate these sessions. But today we have Graham Stevens with us. It's going to be talking about using antennas with Ansys simulation software. So thank you so much, Graham, for joining us, and thank you to everybody who's joining us on YouTube as well as live on Zoom. We're so happy you're here. I wanted to drop one of our featured resources into the chat here. It's an ebook, 8 Reasons to Start Simulating Today. Please check that out. We have a ton of content on our website that can help you with simulation and Ansys software and so much more for your manufacturing business. So be sure to check it out. I also wanted to invite you all to our upcoming Manufacturing Leaders Exchange workshop. We have quite a few workshops coming up beginning in March, and then we have a few that are live and a few that are going to be hosted in a webinar. This is a space for you to talk about real happenings in the digital manufacturing world, successes, failures, strengths, and weaknesses. So join the conversation and stay tuned to see what other cities we're going to be at. We're going to be in San Jose, and we're looking to be at more cities. So be sure to check that out. And after this session, you will get a survey. It should take you automatically to your browser for a survey. So be sure to fill that out. You can send us content suggestions, any feedback. We're happy to apply any feedback that you send us and how we can make these sessions better. And I will let Graham take it away.
Cool. Thanks, Christina. Kristen, this is Graham Stevens. So I'm an application engineer here at KETIV, focused on Ansys products. I've got 25 years of product development, consulting, and simulation experience, and I provide application support for the Ansys high frequency and low frequency electronic applications, as well as optics. And today we are talking about antenna design. My purpose today was to give you sort of an introduction into all of the different types of antenna design workflows that Ansys software offers. In particular, HFSS is what we're going to be focused on today. And it's to typically address these types of goals relative to doing antenna design. So of course, on the antenna realm, we're looking at performance in terms of range, polarization, gain, efficiency, and so forth. We want our antennas to work when there's interference or obstacles. We might have power level concerns or efficiencies concerns, and then of course space. Where is this antenna going to go? Is it aesthetically pleasing? Is it going to fit on the performance side? And then we of course want our antennas to be safe and reliable. So there's a number of standards that one might have to comply with, or you may want to look at thermal reliability, structural reliability, EMI, EMC. And then of course, looking at costs. How much is this antenna going to cost in terms of prototyping or operations and development costs? And so these are sort of, the typical sometimes competing goals that we're trying to satisfy. Ansys HFSS software can allow us to meet some of these challenges. And in particular, antennas, their typical performance is affected by its environment. So its orientation, whether there are nearby objects, whether there are other antenna nearby, its thermal environment, if we're in a spaceship or a satellite, you've got different environmental considerations there. Electrically, does it work with the rest of the system? And then manufacturing tolerances. All these different things can affect the operation of the antenna. And this is where HFSS and Ansys's multi-physics capabilities really shines in terms of allowing us to evaluate all these different factors and make sure it's going to perform as we need it to in the environment it's designed for. And so we're using simulation, in particular Ansys's HFSS software to overcome these design challenges. So with HFSS software, we can actually visualize, as you can sort of see here in this slide, visualize the fields, visualize what is going on over time. We can visualize the antenna's radiation pattern, its gain, its, what does it actually look like, even though the EM fields, of course, are invisible to our eyes. And this allows us to look at the antenna's performance before we've ever built the antenna in the first place, which allows us to modify the design, improve coupling, improve signal and power integrity, and hopefully if the simulation is very accurate compared to what the actual prototype does, you can eliminate our design build cycles. So rather than having to build a prototype, see how it performs, and then modify it and do another cycle and another cycle to get it to perform, we do all those cycles inside the computer much faster, and we can get to market faster. We can reduce the total number of prototype builds, improve performance, and improve time to market. So this allows us to also do design validation for regulatory compliance prior to the tests as well. And allows us to build better products because we can see what we're doing better. So for this webinar, I am covering antenna design workflows. And the agenda is sort of this list here. So we'll first cover what are the primary HFSS platforms and how does that work. There's a short few slides on using Discovery for initial antenna design. We have some auxiliary tools that you may or may not be aware of, different HFSS solvers that, again, you may not be aware what applies. Why would I go to this solver versus that solver? Different antenna workflows where we have an infinite antenna array versus a finite antenna array. There's a bunch of different design options that we have within the Ansys software suite. And then once we have our initial antenna designed, we might want to optimize it. So what are the options we have relative to design optimization, tuning the antennas, and feed of the antennas? What about placement? When I'm having an antenna and it's near another antenna, how does that work? If it's near other objects, how does that work? And what is its performance there? And then finally, some other examples that might be useful. And so with HFSS, and we'll be talking only about HFSS for the rest of this webinar, there are two main platforms. One is called HFSS. It might be kind of the classic HFSS, and it's got a mechanical CAD interface. You can sort of see it up here. It's a 3D, full 3D antenna and modeling tool that pulls in MCAD parts and uses them to model what's going on with your antenna electrically. And you can do all these different kinds of solving. So fundamentally, it sort of started out as a finite element solver. And then over time, as it got more capable, we have an IE solver and an SBR plus solver and a transient domain solver all got added to HFSS. And we'll discuss these in a few slides in terms of what it applies, which ones applies in what situations. And then a secondary interface called HFSS 3D layout was created to make it easier and simpler to import 2D PCB information from traces directly from ECAD software where it was maybe designed elsewhere, and pull it into HFSS into this platform called HFSS 3D layout. And using that, you have the same solve engine for HFSS essentially, but it's slated towards this sort of planar situation. So we have a planar EM solver, and then other links to SI wave and power integrity analyses or EMI, EMC analyses, which we will not be covering today. We're going to focus mostly on antenna design. So as we are thinking about our initial design task and we're getting started and we say, okay, we have an antenna and we want to do X. One of the new options that Ansys has is called Discovery for doing some of these preliminary analyses. So we might start with HFSS and do some standalone antenna simulation. But Discovery will also allow us to do rapid, but not necessarily the most precise analyses, to do very quick and dirty analyses, essentially in terms of if I have a complex housing and how is that going to impact my antenna pattern. We can do some analyses in Discovery to get a preliminary idea of how all that would work. And then, of course, we come back to HFSS for final verification simulation and higher fidelity. But I did want to alert you that Discovery is another tool out there that can be used for this kind of preliminary analysis. And so this is what Discovery looks like. It looks a little bit more like a standard CAD tool, like SolidWorks or SpaceClaim, if you're familiar with those. And essentially, you pull your CAD information into Discovery, assign materials, assign some simulation options in terms of what frequency and what you're looking to do, and get initial results pretty quickly. We can also in Discovery take our original covers and so forth and simplify those to reduce the total number of TETs and complexity of the analysis to again get a very quick and dirty fast analyses. And Discovery makes that kind of simplification very easy and sort of what it was designed for. And so with that, we can get far field patterns, compare them to with and without a housing, and again, get a good feel of what's going on. And you can sort of see how the initial results are pretty darn close, but not precise. And then do a finalized run within HFSS. But this allows us to do sort of rapid determination of design trends much more quickly, which can be helpful as you're designing. So in addition to Discovery, that applies at the initial design stages, I wanted to just alert you to some other tools in the tool shed, essentially. Within the ACT extension realm, if you're in HFSS and do view ACT extensions, you'll get to these. There's an antenna toolkit, which has pre-parameterized standard antenna templates. And that can be very helpful. If you just want to sort of grab an antenna and go, you can do that. There's also an ACT 5G wizard, which has a fully operational kind of 5G antenna project with a solution that allows you to calculate maximum permissible exposure and cumulative distribution functions for a given input relative to the beam characteristics. So that's useful if you're designing in the 5G realm. And then there's some additional toolkits here from the HFSS menu. Toolkits, there's a wavelength calculator. It calculates a wavelength for a given material and wavelength. And then for finite arrays, a beam angle calculator. So I just wanted you to be aware of those tools as you dive in as well. The antenna toolkit in particular is very useful because you have a fully parameterized toolkit. You just input the couple of the dimensions for the antenna and the substrate, and boom, you're done, and you have an antenna that you can then use in your analyses. So there are 50 plus topologies. I won't go into all of them now. You can sort of see a picture here on the left, but standard helical design, standard all sorts of different antennas here, bow tie, dipole, etc. And so then relative to the different kinds of solvers, HFSS sort of started out as a finite element analysis tool, and that is used sort of in this less than 1 wavelength to up to 10 wavelengths regime. So very small size, what's going on at the smaller scale. But when we get to larger analyses and larger pictures of what's happening, there's an integrated design method that's fast method of moments that's used up to 100 wavelengths roughly. And this is very useful, especially if you have a lot of metal and not as many dielectrics around. But so if I've got an airplane surface or the surface of a satellite or something, the method of moments can be very useful. And when we get to even larger realms where we're looking at battleships or cities or much larger arenas where we're up to 10,000 wavelengths in size of analyses, we have something called the SBR plus solver that's used for those situations. And as you can see here in the graph, there's also something called domain decomposition method, where if we have a very large and complex model, we can chop that model up into pieces and solve those pieces separately, perhaps with high performance computing, where you send each piece to its own solver, to its own computer or its own core to be solved. And that allows us to calculate and handle very large models of very complex models. So just be aware of these types of solvers so that when you have a problem in one of these regimes, you're kind of focused on the right kind of setup and type of workflow that would be most suitable for your job. Just to kind of dive into the solvers a little bit more, the finite element method solver is a full wave EM field solver. It meshes in a finite volume, and it uses a tetrahedral automatic adaptive mesh, where it is meshing more finely in areas with higher gradients and where it's needed, but less finely elsewhere. And it does adaptive passes where it'll do an initial pass and measure the error, and then it'll add more mesh in the places where it has more error and keep going until it gets to a certain error percentage. This makes meshing much easier than in the fluids or the mechanical space. You basically don't have to think about it for the most part. Just let HFSS do its automatic meshing. There's some exceptions to that, but that's pretty much true. And then this allows you to solve EM fields, again, at this kind of 0 to 10 wavelengths range. The integral equation solver uses the method of moments techniques to solve for sources and currents on the surfaces of conducting and dielectric objects. And it's especially efficient for large metallic structures. So if you're looking to do an initial design and your antenna is made out of metal and what's around it might be made out of metal only, the method of moments, i.e. solver, can be very efficient and a much faster way of getting initial results. So you might consider this as well for doing some initial designs. And then finally, as we get to larger sizes and we need the physical optics solver, we start propagating the electromagnetic waves modeled as rays rather than a full wave EM solver as in finite elements, and make that approximation at the larger scale. And that physical optics solver basically became known as the shooting and bouncing ray, the SBR solver, which is an asymptotic technique useful for very large spaces, and it extends physical optics to multiple bounces. So it traces the ray as it goes through the design. This allows for different materials, and then there are some more fine gradations built on the SBR plus relative to diffraction and what happens at edges. And so there's edge correction, edge raise, creeping wave, a bunch of other techniques to improve analysis results when that is in the field of view. But essentially you're painting currents on the bodies and radiating those painted currents to field observers. And all this, of course, improves accuracy in the large scale. In addition to those different solvers that we were just covering, there's ways to hybridize them. So if I need to use the finite elements for right near my antenna, and then I want to get a far field pattern further away, I might have an IE region in one spot and a SBR plus region in another spot, or a PO region. So these are ways to mix and match the different solvers for sort of the different arenas that they solve well in, so that you can get a total runtime for your simulations that's both accurate as well as getting you an answer as fast as possible. And then HFSS itself also has a transient solver built in it as well, where you can do TDR analyses, etc., to get a sense of what's happening for transient analyses. So we can get, do the impact of lightning, we can do TDR analyses, etc., at the transient in the time scale. So this picture here is a design workflow for a 5G phased array. It's a broad picture, and I'm going to take this and sort of broaden it out a little bit more and expand on each of these elements. Some of these may or may not apply to your design, which is fine, but this is sort of a broad brush structure of how an antenna array might be designed, and what are some of the steps that you might go through. And for each of these, we'll go through different workflows and different ways to accomplish each of these subtasks, so that we can get a better feel for which workflow applies to what I'm trying to do. So we start here with antenna element and array design. So we start with designing the initial element, and then maybe expand that to make multiple copies of that element in an array. We then might use SBR Plus to take that array and install it somewhere, and then see how it interacts with the rest of its surroundings. We might want to take a look at, if I have multiple antennas around at the system level, take a look at link margin or interference or coupling models. How do these two antennas talk to each other or couple? And then at the much larger scale, if we're thinking about a cell phone network or some other kind of network, we might have network planning and coverage studies. This, of course, will not apply to everybody. And then finally, we might have some multi-physics analyses where we look at temperature or structures or two-way coupling of these things to get a sense of, well, how would temperature impact my system analysis? How would it impact my antenna analysis, et cetera? To get a feel for, does that impact my design as well? And so we'll now sort of dive into these individual sub-buckets, so that you've got a good feel for which types of analyses or which types of workflows would apply to each of the situations. So when it comes to phased antenna arrays, HFSS has a couple of different approaches. Generally, we sort of start with the unit cell approach, where we just model the unit cell for the phased antenna array, and we assume that that's an infinite array of that particular element. And when you do that infinite array, it's an approximation. The edge effects are ignored. You have a uniform magnitude excitation, and we can analyze that much more quickly, because we don't have to it's less of a computational job. But the accuracy, of course, it does ignore these edge effects and so forth. So that's an issue potentially. But for our initial design of our initial element, this unit cell analysis is very useful. And then, of course, on the far right here, we can take that initial design and expand it. This is a 7x7 entire array, and we can explicitly model each one of these individual elements, and then look at the edge effects and edge treatments and get mutual couplings and arbitrary excitations. So we have very complex geometry, a large number of excitations. HFSS can handle that and model it, but of course you get very high accuracy, but it also takes longer. And in between these two extremes, Ansys created another type of workflow called a finite array DDM, where essentially you model the single element, but it makes a certain amount of certain assumptions around how the coupling is affected in terms of the each individual element-to-element coupling. So we are taking into account edge effects and mutual coupling and arbitrary excitations, but we're only modeling a single element. And as a result, we have much less computation to be done. And we can still get pretty close to what the explicit analysis would show us. And this is another method that you should be aware of. As part of that finite array, well, we'll cover this in a little bit. So in terms of array element design, we have within HFSS, you can sort of see this is a design within HFSS here, where we've created these relatively primitive shapes. We have a coax cable here. We have the feed mechanisms and the antenna here. And then each of these individual shapes, you can create a variable to govern, say, the diameter of this coax cable or its length, and then be able to parameterize and configure this design that way. And then for those parameterized variables, we can do a design of experiment directly in AEDT to optimize the design parameters, maybe do a tolerance analysis, look at the response surface of this, to again sort of get a good feel of how is my initial antenna element performing. Another broader way of thinking about this as well is when I have an antenna array, I can a new workflow that Ansys created is something called mesh fusion, and that applied to the antenna realm. It's called 3D component antenna array, where essentially we've taken the 3D component technology where we just say, okay, the corner piece is going to look like this, and the center piece is going to look like that. And I have multiples of those center pieces or corner pieces, 4 corners. And I'm only going to model those 4 sections. And I'm going to split out how that particular model is. So with 3D components, I can take both geometry and excitations and boundary conditions and separate them, lump them all into what's known as a 3D component. And then that 3D component is meshed separately. And the innovation for mesh fusion is to allow different types of meshing to happen concurrently in a design, where the mesh does not have to be conformal and it can handle that. And this allows us to do very large designs mixed with very small things. And you can mesh all of these things in parallel, so it gets to be faster as well. So please be aware as well that this 3D component methodology is sort of a sub piece of finite array DDM. If you take these pieces of your array and make them into 3D components, you can again go faster because it can parallelize things more. So that's in general how we go ahead and design our both element of the design and the phased array. And now when we start talking about antenna performance, you typically would analyze antenna performance using SBR plus, where we're in sort of that larger space, where we're getting away from just right near the antenna where you might have one or two wavelengths, but now we're larger array. So this here you can sort of see is a cell phone tower with a number of antennas. And we can start looking at performance using SBR plus. So we have fully coupled, we're using shooting bouncing rays from each of these antennas to see how they interact and what's going on. Perhaps hybrid solutions relative to using finite elements right near where the antenna is for the array, and then out to the larger coupling matrix for SBR plus, and again, looking at sort of antenna patterns for each of the antennas and how they interact. Yeah, so I just want you to be aware of this, that SBR plus is a way to model these sort of situations where you have multiple antennas interacting with each other. This is kind of an example of looking at the coupling between all these different antennas on a cell phone tower. So we can get a good feel for that. We can also go back and take a look at, well, if I were to change the radome or change the housing right near the antenna, what's the influence of that on my radiation patterns? So we might do some radome analysis. And this is where you add the radome into my 3D component or FEM results. And then we can start looking at the antenna patterns that result of with and without radomes, or if I change the radome in some fashion, what happens. And then when we have multiple antennas and we're looking at things like link margin and interference, we might take that SBR analysis and use something called emit to take a look at that situation. So more closely, and emit, of course, takes transmitters and receivers and how they interact and does RF cosite interference analysis. And so this is another auxiliary tool that's part of the HFSS universe that you should be aware of when you start to think about how antennas interfere with each other. And this allows us to calculate link margins, look at the interference. You know, what happens if my distance changes or my placement changes? What happens if my, you know, the inside of my antenna changes in terms of some variable here? How does that impact my interference and coupling, et cetera? So we can do this at the kind of room level, at the city level, at the battlefield level, and get a better sense of how these antennas will affect each other. And of course, look at link margin versus distance, you know, with and without interference. And then building up to, well, if I have a really large number of antennas and we're looking at network planning and coverage, we have multi-user, you know, MIMO type analysis. We're evaluating channels. HFSS can also handle this kind of thing where we're looking at base station handoff, receive power, coverage zones, et cetera, and start to get, you know, much larger systems. And then, as I mentioned before, when it comes to multiphysics, what happens if I change the temperature? Will that impact the antenna? That changes the size of the antenna, which then might change its resonance, et cetera, or gain. What happens if it's under stress in some fashion structurally? And you might need to do two-way coupling along these lines as well. So maybe the temperature impacts the conductivity of the copper, which then impacts the performance. And so you might need two-way coupling depending on what kinds of temperature regimes you're talking about. And same thing on the structural side. So this is sort of an example of two-way electrothermal simulation of a 4G base station antenna. There are a couple of different methods to do this. We can do it kind of within Workbench with this feedback integrator for doing these kinds of solves. We can also do some of this within AEDT, where we have, say, IcePack is our thermal solver. So there are some different choices in terms of what kind of thermal solve you want to do and how you want to connect these things. If you get to these kind of analyses, please do just email support@ketiv.com. We'll be able to help you decide which way to go and why when you get to the multiphysics side. And then we may also, part of the whole purpose of doing simulation is to optimize the design in the computer before we even produce the part in the first place. And within the Ansys universe, there are a number of different ways to do that. On the geometry creation side, you typically would create the geometry inside HFSS with using primitive Boolean operations, and then name parameters there. That's generally the easiest and fastest way to do parameterization in AEDT and HFSS. You can also use discover your space claim to parameterize varying geometry parameters, and then change those things either in Workbench or in AEDT, and look at parameterization studies. So as I vary a thickness, how does that change my antenna performance? If I change a length here or a length there, how does that change my antenna performance? But when it comes to multiple variables and trying to figure out, okay, if 10 different variables all could impact my design, then we might start thinking about some of these other techniques on the right here. So we can apply derivatives and do a tuning exercise. We can use optometrics to run parameterization or optimization studies. And finally, we can use OptiSlang to run optimization studies. And I'll cover the whys and wherefores in the next few slides. One thing we can do is called analytical derivatives. And so within the solver settings, you have your different variables that you've set up, and you call out, I want to take a derivative of each of these variables. And based on the derivatives, you can do with this report tuning here, where I basically have a slider bar where I can say, okay, I'm going to change my feed position or my patch length, and just do a slider, and it will then recalculate pretty quickly and allow you to sort of see the impact of changing that variable relatively live, so that you can then use these slider bars to sort of get a feel for, okay, what rough range do I want to be in? Where do I want to maybe do some more finer tuning analysis and dial in more? And that allows you to sort of quickly explore the effects of the small changes on S parameters or radiation patterns, whatever antenna output you're interested in. Just requires a little bit more setup in terms of calling out these patch lengths and which derivatives I want to do, and then setting these report tuning. So that allows you to sort of get a feel for what's going on in terms of the design. When I want to dive in a little bit further and now optimize, there's something called optometrics. There's a whole host of different options within optometrics. I'll start with sort of parametric analyses, where you're sweeping through a range. So variable X is going to 1 to 10 to 5 to 6, and what's the impact on the design? You can just run multiple analyses and see those impacts. We can then do a design of experiments where we look at a response surface or a goal-driven optimization. Design Explorer is a tool that's kind of from the mechanical realm, that allows you to kind of go back and forth there in Workbench, doing some of the kind of a similar types of optimizations. There's an optimization tool in the optometrics area within HFSS that you can set a cost function where you say, okay, I want to minimize my cost to get to a certain frequency at a certain dB of my S11, and now we can optimize to that and have the computer change the variables on the fly to get to try and meet that goal. Tuning we already covered, and then there's some statistical analyses as well. So all of these are different types of analyses that you can run to optimize your antenna as you go. And then finally, there's one last option here called OptiSlang that's at the very top. And this is where OptiSlang has these kinds of optimization tools, and you can sort of think of it as optimization on steroids. So when you have tons of variables, when you have a harder optimization problem, the optimization algorithms within OptiSlang are designed to, instead of brute forcing things and running 1,000 simulations to figure out, where do I need to play here? It allows you to make inferences on those, run only a few simulations, make some inferences, make sure, and reduce the total number of runs to get a similar result. So I might have 50 runs or 100 runs needed rather than thousands. So this can save you a lot of time when you're trying to optimize as well. And so the way it does that, of course, is it starts with looking at sensitivity analyses and a sensitivity study to figure out, well, which variables actually make a difference in my design, which ones influence what. Then based on that, you reduce the total number of variables you're actually modeling, and then do what's known as this meta modeling, where again, it will model a few cases, up to 50, 100, maybe 500 cases, and then get a really good sense of which variables are actually changing the design to get you to your cost function, or get you to your optimization goal, and do design improvement. A little bit later in the design cycle, you might be interested in more robustness or reliability, where you're looking at Six Sigma design and manufacturing tolerances, or some sort of Monte Carlo analysis. And OptiSlang can help you in that arena as well. So this is just an example here on the satellite side, where we might have a satellite antenna. We're looking at gain, directivity, bandwidth, polarization, feed type, and steering. We have used, in this particular case, the antenna toolkit relative to designing these antennas. I pull in my satellite geometry, make it all metal, or the equivalent for your solar panels here, and then start doing an SBR plus analysis to really get a feel for what's going on in the far field with these different antennas. And then similarly, I can start looking at, well, if I group these elements into arrays now, and start looking at steering, what do those fields look like? Maybe use the finite array beam angle calculator to help guide you in that design. And then use SBR plus to look at installed performance and antenna coupling. And then co-site analysis in terms of what's happening, how are my different antennas interfering with each other or talking to each other, and mitigate co-site response with filters or frequency planning, or change the placement of the antennas. Enables you to sort of see it before you design it. And we are now at the end. So my final conclusion here is that Ansys can really help solve your antenna design challenges in the computer before you ever get to manufacturing. And at this point, I'll just pause here and stop for Q&A. Wondering if anybody has any questions. Okay, well, with no questions, I just wanted to talk a little bit about other additional resources and where to go from here. So this was sort of a broad brush introduction to HFSS and the different types of antenna analyses. And so there's a lot of different resources to help you get started. So the very first one I wanted to introduce is if you just email us here at KETIV at support@ketiv.com or call us. We're happy to offer additional support in terms of guiding you through, I'm trying to do X and I need some help figuring out how to do that. What courses should I take? What information do I need to get there? That's one of the things we're here for. And then within something called the Ansys Learning Hub, there are a number of courses here that are applicable. So there's HFSS Getting Started. There's HFSS 3D Layout Getting Started on the two major platforms. There's the Discovery Learning Room if you're interested in using Discovery. And then an antenna design course that goes through each of those individual types of workflows in terms of, say, an infinite array analysis or a finite array analysis, et cetera. And SBR Plus as well. And then in addition, I wanted to alert you to the HFSS online help. The little question mark at the upper right is very helpful. And there are also, if you are within HFSS, just in the file menu at the upper left, if you click on that and go to Open Examples and HFSS or HFSS 3D Layout, there are a number of example models that are there for you that sort of show you how it's done. So if you're looking for a particular type of antenna or a particular type of analysis, this is another fruitful thing in terms of taking a look at, well, what's the example model look like? Ansys also has a how-to YouTube channel here that's recommended. There are also webinars, which you can sort of see here in the Resource Center. And then finally, in the Ansys innovation space, there are free courses under this website here, courses.ansys.com, which also has really good tips and tricks and courses and ways to get started. So I just wanted you to be aware of all these different ways to get started, and then please do just email us if you're swimming in these and you want some help. In addition, KETIV offers simulation services. So if you have a design and you don't have enough time or you don't have the expertise, we're here to help as well. So we're happy to solve your problems for you, help you solve your problems, train you, have you do your problems 100% and give you support, anything in between. So we offer simulation services as well. Just wanted you to be aware of that. And with that, I think I'm finished. Thank you so much for your time, and I hope you have a good time simulating antennas.